Hello, everyone, and welcome back to Two's Complement, the series where we are converting the One Lone Coder's pixel game engine from C++ to C#. My name is your host, Propagating. Welcome back to the show. Apologies for the very long delay in getting this episode out. I had some health things that I need to take care of, along with school and work, and that's all taken care of now. So we can go ahead and get back into this, and I'll try to get back into the swing of at least one video a month. Maybe more than that. I don't know. Big shout out, thank you to JavidX9 and his One Lone Coder project for allowing us to use the Pixel game engine for this series. You know, even though we're not supported or endorsed by him in any way, you know, it's still really great that we have permission to use this. Use this engine that he's developed and worked on over the last couple of years. So big thank you there. Links to his stuff are in the description as well as on the GitHub for this project. Go check him out. Check out his series. They're really good. And especially the series on the Pixel game engine itself, it'll be invaluable if you're following along with this conversion process. So with all that out of the way, what were we talking about? Last time we talked about the resource packs, adding files to the resource pack, saving them to disk, loading them back in to memory, and doing things with them. You know, pretty basic stuff at the end of the day. Everything was stored as a text file. We weren't worrying about compression or anything like that. But we left it with the scrambling features incomplete. And I was a little stuck on whether we should go ahead and just implement the scramble method exactly how it is in the C++ code, or if I should alter it into something that is a little bit more robust as far as file protection, and that still stays within the C#, kind of the core .NET framework without needing any outside packages. And I think that we can do that. And, you know, this is a case where we're following the spirit of the code, not the letter of the code, because the point of scrambling the file in the original implementation was really just a very basic form of encryption. So that's what we can see highlighted here is we're taking a key that someone passes in. We're doing a very basic XOR replacement for each byte in our file. We're doing that in order, and we just kind of loop through each byte of the key. And because XOR is a symmetric operation, we unscramble it by XORing the same values again. If you don't believe me, you can play with that in your own time in binary. Just get, whatever binary numbers you want, XOR them, XOR the result with the same key, and you'll get what you originally passed into it. So with that said, I felt that because the goal is some basic level of encryption, we should try to achieve a basic level of encryption in C#. So what does that look like? Well, let's go ahead and show you. What that looks like is implementing an encryption method and for saving, and a decryption method for loading the file. And how we do that is we're going to be using AES encryption. It's built into the .NET framework. It's a form of symmetric key encryption. What does that mean? It means that we use the same key for encryption and decryption. It's not like RSA where there's a public and private key that you're passing around, where it's using the same key. We're going to be using AES 256. 256 refers to the bit length of the key itself. That does not mean that you need to pass in a key that is 256 bits in length or 32 bytes in length. It just means that we are going to transform whatever key is passed in to be 256 bits with a key derivation function, but that doesn't really impact it. So what that means is you can have any password essentially that you want for your key, and we will convert it into a compatible byte array for our encryption needs. So that's really awesome. And without anything else, I don't think we really need to cover any more anything else. We can go ahead and dive into how we've achieved this, right? And on screen, you'll see that. Actually, let me go back to the parent method. So essentially, what we did is we created a save resource and load resource parent method, public method, whatever you want to call it. And essentially, what this does is this is just selecting, allowing the user to pass in a configuration for the type of protection mode they want, which is just an enum. We can look at that if you really want. We've got non-encrypted and scrambled as, just in case we do want to implement that in the future. And then we have an optional parameter as our key. Obviously, we will need the key for our encryption and scrambled functions, but we won't need them for our plain resource pack. So if you pass in a key but still choose no protection, then the key is just, we don't care about it. So say we do want our packages or our resource pack to be encrypted. We do some very basic validation. We delete any existing files that has the same file path that was passed in, and then we save our encrypted resources. So as you can see, this is a fairly small function at the end of the day. It's not really that many lines. It's what, 30, 40 lines, which is relatively small. Because there's not really a lot, C# makes it really easy to actually implement this kind of encryption and decryption, just with everything that's built into the language. I think that is one of the benefits of C# is that because it's got this very robust standard library in the .NET framework that has a lot of these nice functions that we can take advantage of. And I really want to take full advantage of the language features here. So that's what we're going to do. So what do we do? What do we need to do in order to encrypt a file? Well, first thing we need to do is we need to create an AES object. And then we need to initialize some values. So you can either generate a key or you can pass in a key. In this case, something that you need to be aware of is that if you do generate a key, you need to save that somewhere and you need to hold on to it and you need to be able to pass that back into the object. I do not recommend generating a random key and saving it and trying to work with that. I would very heavily recommend passing in and creating a key that you know and that you can hold on to in your own time. Use a password manager or something to generate it. I don't care how you do it. I just would heavily recommend not just generating a random key. But that said, we can't just pass in a string and then let that work, because this key is a byte array of a specific length. And thankfully, we don't need to specify the length of the key, as long as the key is one of the supported lengths, which is 96, 128, and 256 in the AES standard. The AES object will adjust accordingly. Now, there are other forms of AES that have a larger key size, but they're not part of the kind of the original AES standard. So we're not going to worry about that. We're just going to use a 256-bit key. So how we translate that key, a string, into a usable key is through a basic transformation method. And essentially what we have is a key generation algorithm or a key derivation function that is built into the language that we can run. And essentially what this does is it takes in a password. You can pass in a salt. I don't believe it's required, but we do have a salt that is created. This is just an 8-bit, 1, 2, 3, 4, 5, 6, just an 8-bit 8-byte salt that I created. Just kind of randomly choosing some things based on prime numbers. I can't remember exactly what I did. It was overly complicated and altogether just not really worth the time. But here we have some good numbers. Use a different salt. Use whatever salt that you want. The reason that we do this is so that way the same key being used on multiple machines, as long as it has a different salt, will have different outputs. The salt can be public. It doesn't really matter if the salt's public or not, because even knowing what it is, it's not going to help you actually, break the encryption or break the key just by knowing the salt. So we pass in our string password. We pass in our salt. We need to provide a certain number of iterations for our key derivation function to run. I believe, before this used to be like a very small number, like 10 or 20,000 iterations. This is recommended to go up to like 100,000, 300,000, somewhere in the 100,000 ranges from what I hear. So because of that, I just chose, 655, 360, which I believe is a power of 2. Anyway, it's not all that, it doesn't matter all that much. Point is, use a large number for iterations. I'm using this is what I'm using for my iterations. You can use a different number if you want. And then we need a hashing algorithm. We need to provide a hashing algorithm to our derivation function for generating a cryptographically secure key. In this case, I'm using SHA-512. It's cryptographically secure. And you can use something else if you want. I would just make sure that it's a secure key. Like, you don't want to be using an MD5 hash, for example, in this case. If you may get some warnings here, like if you don't pass in a hashing algorithm, it'll say that the default implementation is obsolete and is not really secure. So you need to pass in a new hashing function. You can't just use the key derivation function as it is without that. So we let our key generator run for however many iterations, and then based on what it returns, we just select 32 bytes from that value, and then that becomes our AES key. And the nice thing is that this is all deterministic, so obviously it needs to be in order for our encryption and decryption to work, and to ensure that we get the same key every time. That we pass in the same values, we get the same key. So that's important. So once we've transformed our key, we can set up some more of the AES configuration settings. So first thing that we're adding a padding mode. And essentially what this is AES is a block cipher. What that means is that data is encrypted and kind of spat out in blocks that are 16 bytes. It's a 4x4 matrix. And if your data isn't aligned to that 16 bytes, AES needs to pad your data with some kind of nonsense values in order to have a properly encrypted object. So that's why we have our padding. This ISO padding is just a random string or random string values, which is nice because what that means is that every time we run the encryption, we'll get different values. And we don't run the risk of having the same encrypted text being spat out every single time. Next thing that we set is our cipher mode. In this case, I chose CBC. And the reason that I chose CBC is that this also allows for, what this allows for is that you can have the same data being passed in to the AES encryptor, but it will not always return the same encrypted output. So if we were encrypting the string, the quick brown fox or whatever, the quick fox jumped over the lazy dog. Every time that we encrypted it with this cipher mode, we should get different values. And that just makes things a little bit more secure and a little bit harder to identify if the resource packs are identically the same, even if they're the same size. At the end of the day, the encrypted content will look different, even if the underlying unencrypted data is identical. So that's kind of why we choose this padding and encryption mode. Next thing that we need to provide is an initialization vector. And what this is, you can think of it like a seed for the encryption function, because without that, the encryption would, the encryption function would essentially behave like a random number generator that is always running on the same seed or with no seed. And if you've ever done that, you'll notice that the numbers from the RNG are always coming out in the same exact pattern. It might be like 1, 3, 8, 7, the first time. And then if you reran the program and use the same RNG but didn't provide a seed, you get 1, 3, 8, 7. But by providing an initialization vector, which is, again, it's a 16-byte block to match the block size of AES. By providing this initialization vector, you're essentially telling AES to start at a random location and to move on from there. And that also is another layer of security in order to ensure that the same data being passed in to our encryption has a different output every single time. Now, this initialization vector is kind of like a salt as well, in that it's okay that it's public. And in fact, we need it to be public and we need it to be stored somewhere. So that way, when we decrypt our data, we know the initialization vector that was used. And we use the same initialization vector when we create our decryptor. So what we end up doing is we actually end up writing our initialization vector to the beginning of the file, and we do not encrypt it. We write it as plain text before we start writing our encrypted text. So that's what is going to happen. So before that, though, for ease of use, what essentially I'm doing here is I'm writing out all of our binary data, and this is what we covered last time, but I'm writing out our file into a byte array. And the reason that I do this is so that way we just have this binary buffer that contains all of the data that we need to encrypt separately from our initialization vector. And then we can just hold that in memory until we need to write it to a file. So we do that here. We write everything to our byte array. We create an encryptor object, and then we create a file stream to create a new file. We write our initialization vector to the start of the file, and then using the crypto stream, we write the rest of our data to the file itself. And then we flush our streams and we're good to go. Now, you'll notice that I have this deprecated start position thing here that is not actually being used. And initially, I had a bug in my code in that I was trying to account for the offset caused by writing our initialization vector to the start of the file. Meaning that because this is adding 16 bytes to the location, I thought that we would need to increment the start positions of our offsets by 16 bytes. So, if the unencrypted version stored something at location 370, the actual position in the file would be 386 because we have our initialization vector. The funny thing is that we don't actually need to do that because of how the streams work. Essentially the offset is based off of wherever the stream was created, and you tell it was its starting position. So we it basically accounts for that offset automatically. You know, and we might see this, it might be a little bit easier when we load in the file to kind of visualize that. But essentially what happens is, because we wrote the initialization vector first, its stream, you know, sees itself as containing the initialization vector. However, the crypto stream and our binary writer, they're already offset. They already have built into the offset. Like, they think they're at position 0 when they're really at position 16 in the file, and they'll just write from there. So what that means is that when we load our data, we load in our initialization vector, and then we create a new stream at position 16, and it's also thinks it's at position 0. So we don't. It's already offset for us, basically. You know, I'm sorry if that's a little bit hard to visualize. I don't think. Let me just double check if my drawing pad is. I don't think my drawing pad is working at the moment, so I don't know if I can. I don't think I'll be able to. Yeah, I'm not going to be able to kind of draw this out for you at the moment, but just kind of think about it as the, you know, even though it's at position 16 in the file, the position of the stream is at position 0. So it's already accounted for the offset. We don't actually need to worry about this start position at all. So we can actually go ahead, you know, why don't we go ahead and remove that? So that's our saving function, you know, super simple, not really anything complex going on here. All that we had to do was set up our AES object, you know, create an encryptor, create a new crypto stream that takes in that, and then write our data to the file, you know, and that's it. You know, we didn't need to do anything else. Now let's go to our load function. And this is basically doing the same thing, but in reverse. The only difference here is that we need to read our initialization vector out from the file before we start. So how do we do that, right? Well, first, this time we need to open our file, obviously. So we create our file stream. Then we're going to go ahead and create our AES object. Really, you know, you could create this AES object first. It doesn't matter. Kind of, you know, these using statements can be swapped if you like. It really doesn't matter. And then we need to, you know, we need to specify the same padding mode, the same cipher mode. We pass in our key, you know, our transform key. And then we need to grab our initialization vector from the start of the file. So what we're going to do is we're just going to create a new byte array that's going to store our initialization vector's data. Obviously, we need to know how many bytes we need to read. In this case, it's always going to be 16 and our current position. So then we just run through and read one byte at a time until we reach the end of our initialization vector. Once we have that, we tell AES, hey, this is our initialization vector, go for it. And AES will do it, you know, and we're good to go. So now we need to create another crypto stream, but in this case, we are reading the data and we have a decryptor instead of an encryptor. And I'm actually going to go ahead and spit this out just for ease of use. Oops, did I spell that? Decrypt. Yeah, no, that's correct. Why is it getting whatever? Looks like my spell check is off. Anyway, we go ahead and create our decryptor. And what you'll notice, right, is that when we're creating our crypto stream, we're creating it after, you know, after we've read and advanced our position in the file by the length of our initialization vector. So, you know, now when we're reading this, it thinks we're at position 0 well, basically we're at position 0 in the stream. Whoops. We're not at position 16 in the stream. We are in the file stream, but for our crypto stream, we're at position 0. And what that means is that when we're reading our data out of this, it's all of the offsets are, you know, assuming that it's based off of the start location of 0. So this is why we don't need to worry about offsetting our data by the length of our initialization vector. Because just like in our save function, this is going to assume it's starting at position 0, so our offsets are going to be based as if it's on position 0, and that matches up. So we don't need to do anything more. We're reading our data, and we're storing it in our binary buffer, and then we create a resource stream from that. And what else do we need to do? Nothing. We have our resource stream, so we can go ahead and call our read binary data function, and this is exactly what we had for our previous load, right? This is going to load in our data. This is going to load in our file map with our resource files, and then we have everything sitting around in our resource stream, ready to create a resource buffer as needed, right? So now we can use these, right? Now we can actually use our data just like we could before. So let's go ahead and run this, and we'll take a look in the hex editor at what the encrypted data looks like and what the decrypted data looks like. All right. Okay, so everything's been written to disk. So let's go ahead and open up our hex editor. We call this encrypted, right? Testpack encrypted.txt. Yes. I'll go ahead and just refresh this just in case, but it should be correct. So what we see here is perhaps a little interesting, but you'll notice that all of our text is garbled. And the only thing that we know for sure is that this first 16 bytes is our initialization vector, right? And this is the plain, quote, plain text or the plain data of our initialization vector. This is not an encrypted string at all. This is the data used to initialize our AES object. Everything else is encrypted. And, if we look at this kind of analyzed page, you'll see that this byte distribution is pretty much constant around each. That's a good sign that it's either compressed or encrypted. We've got, a constant level of entropy. And the nice thing is that this will tell us, hey, this is most likely encrypted or compressed in this text editor. So that's what it looks like when it's encrypted, right? Now, let's go ahead and look at the decrypted version, and I can just show you. Oh, it's not going to show. I'm sorry, it's not going to show my Explorer window now that I think about it. But bear with me. I will open up our unencrypted text, and we now have our unencrypted text. Right? We've got our file length here, which is 252.361. We've got 5 files in our list. We've got the length of our string. We've got our string here. And we have our offsets. We've got file size, and we have offsets. So this should be position 370. No. I am off. 398, wasn't it? Oh, wait, where was I? Hold on. 398, 1, 2, 3, 4, and 370. 398. So yeah, these all worked correctly. What am I? Oh, phooey. Oh my gosh! I'm doing this again. I need to convert that to to hex. So that's position 172. I did that last time, didn't I? 172. There we go. 172 namespace pixel game engine sharp. Yeah, there we go. I have done that way too many times. I'm sorry. So anyway, we have our offsets here. They're correct. We have our sizes correct, and we've successfully decrypted our text, rewritten the files to disk, and there we've got an encrypted and an unencrypted version of the same data. Now, one thing that I do want to point out, right, is that you'll see here each of these lines is 16 bytes, right? And if you remember, AES is a block cipher, and each block needs to be 16 bytes. This, however, is not a full 16 bytes at the end of our data. So what that means is that we need to, there needs to be padding added for AES to finish encrypting the file. So you'll notice that, our initial file size was 252,361 bytes. However, when we come over to the end of our encrypted data, you'll notice that we are beyond that, right? So we're at 3D 9D0, where before we were at 3D 9C0. So we have another, what is that? We have another 7 bytes to finish the block where our data was in, and we have a full separate block following that. So our encrypted data is a little bit larger than our unencrypted data, but not drastically so, right? It's 23 bytes bigger. That's not going to kill anybody. That's not going to, that's totally an acceptable, increase in size. So that's really everything that we need to cover as far as, encrypting our data and storing our data in a protected state when it's at rest. Now, obviously, there are ways that people can get around this. DRM and other protection methods, people have defeated them for years. They will continue to defeat them. There's an argument here that this is really only keeping honest people honest, and that if you really wanted to, you could break into this file structure, especially if you know kind of the base structure. And because this is open source, of course, you're going to know the base structure of these resource files. That's not really the point, though. I think at the end of the day, like if you need to show that, if you've got copyrighted things that you have a license to use, and you just need to show that you're trying to prevent unauthorized use, this is more than enough. This should be more than enough security to say, hey, look, when the data's on disk, it is encrypted. It's only loaded into memory, and used when it's being used in the game, and when it's unloaded, it's unavailable, and blah, blah, blah. It's just something to think about, right? So I wouldn't worry, too much about, oh my gosh, it's somebody can get into our data and blah, 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 because of course somebody can. It's never a question of if, it's a question of when, right? So all that said, there's a question, do we go ahead and implement our scrambling, or do we not? And I don't really know the answer to that. Yes, we could make it backwards compatible with the original version of the Pixel game engine. But at the same time, if somebody really wanted to use our C# version or translate over to the C# version, I don't think it's out of the question to say, look, unscramble your resource pack, save it as plain text, and then use the encryption methods in our C# version of the game engine instead. I don't think that's out of the question to, for support. That said, if this scrambling is not a super difficult thing to implement, so if somebody wanted to, they could easily add this in. It's already stubbed out. It just needs, the code just needs to be written. So that's just something, to think about if you'd like to contribute. That's something that you're more than welcome to do. So this almost concludes our resource loader implementation and our resource pack implementation. But you'll notice that there's this image loader that we haven't touched yet. Oh, and there's also this make POSIX function, which it just replaces the path in from a backslash to a forward slash. We could go ahead and implement this. Why not? Right now, why not? So public string make POSIX path. There. Thank you, GitHub Copilot. So super easy. All we have to do is we need to, just replace our double backslash with a forward slash. And now we've got that built in. But back to the point. I might as well just show you the C# that we just did. I need to remember to switch back and forth. So we've got our string replacement here. Totally easy, fine, whatever. Took 5 seconds. We have our image loader that we need to do for our resource pack. And this is loading and saving our image resources. But you'll notice that this is dependent on the sprite class. And the sprite class is dependent on the generic vector classes that were created in the Pixel game engine. Now, we need to figure out how we're going to achieve this behavior in C#. That's going to be the focus of the next episode. And we're going to talk a bit about some of the different considerations here. Anybody who's tried to make a generic vector class that supports, the numeric types in C# will know kind of the pain involved in trying to do that. With the new generic math, it should be much easier. However, C# has built-in, vector 2s and vector 3s and vector 4s, I believe, or at least we got quaternions. So we might just extend the vector 2 class, and that's kind of what I did. That's kind of what these vector 2 extensions are for. The downside, though, is that these are all floats only. And so here's our extension. So the problem is that this is all float only. This is not like double or integer compatible. But the ones in the Pixel game engine allow you to be doubles or floats or integers. So we need to be aware of that. And like I said, with the new generic math, it should be easier to implement a generic 2D vector type and 3D vector type in C#. So that might be the way to go, but I haven't decided yet. Anyway, that's going to be what we talk about in the next episode. I might also do a bonus where I'm live coding the vector 2D generic type, just because it's something that I've tried to do in the past, at least before the generic math stuff came out. I'd like to kind of learn how to use the generic math, and that might be a good exercise to record, so that way some of the newer programmers can kind of see, one, how do we learn? Two, how do we implement functionality that we haven't been exposed to before? And how do we kind of troubleshoot and problem solve that technology and that functionality? And how do we deduce good information from bad? Because of how much crap is on the internet, that could be a big question. What's good? What's crap? What's gold and diamond and what's not? So anyway, I've rambled on too long about what we'll do in the next episode, but stay tuned. Thank you for your support in this. Again, apologies for the very long delays, but I hope to be getting back into the swing of things shortly. So have a good one, and I'll catch you guys in the next one.